In this video, we will solve a problem involving projectile motion. So this is an in-class exercise for chapter 12 projectile calculations. So we have seen that in projectile motion, particle has motion only along x and y, and the particle is given some initial velocity v0 at some angle theta. So we need to break down this velocity into horizontal and vertical components. So if this is v0 and this angle is theta, then x component of the velocity is v0 cosine theta and y component of the velocity is v0 sine theta. Now let's look at this projectile, motion of projectile. This is from homework 1. Graphical representation. So a particle is initially at this position where x0 and y0 define the x and y coordinates. It's given some initial velocity v0. So v0x and v0y. X and y components can be calculated using v0 cosine theta and v0 sine theta. And then the particle travels along this blue path, which is free flight, and it's subjected to gravitational acceleration, which is acting downward. So let's look at how the components of the velocity changes as the particle travels along the projectile path. Remember that the length of the vector indicates the magnitude of the velocity and the arrow indicates the direction. So as I move the cursor, the projectile goes from travels from point A to point B or from left to right. So as you can see here that when projectile is launched with some initial velocity, Vx arrow remains horizontal, but Vy changes its magnitude. It's getting smaller and smaller. That means y component of the velocity changes or it decreases to the point that where it's exactly at the peak of the projectile motion, the y component of the velocity is 0. And then y component of the velocity changes the direction, and under the influence of gravity, it's now increases in the opposite direction, and the total velocity of the projectile changes depending on the magnitude of Vx and Vy. So once again, remember that there is no change in x component of the velocity throughout the projectile motion. X is always same. Y component goes from maximum to 0 at the top and from 0 to negative as it goes towards the ground. So let's apply this concept to our projectile in-class exercise. So for this in-class exercise, the ball is kicked from point A with some initial velocity 10 meters per second. So, and then determine the maximum height the ball reaches. So that's first part of the question. So let's look at the problem more closely. That the ball is launched from A with some velocity 10 meters per second, and we need to calculate this maximum height. Now, since the maximum height is along vertical direction, we need to use one of the y component motion equation for the projectile. Now, the maximum height is given by y at the given point, and there are two equations that has y in them, equation number 4 and equation number 5. We cannot directly use equation number 4 because equation number 4 also has time t, which is unknown. We do not know how long it takes for the ball to go to the top. So we will use this equation number 5 and apply it between points A and B for the projectile motion. Remember that the entire motion from A to C is projectile, means you can apply the projectile equation between any 2 points along the path of the projectile. So we will first apply the projectile equation between point A and point B. So where A is the initial point, B is the final point, and we write that equation. This equation we rewrite this in the form of A and B, where V0 will become VA because that's the initial point, and Y will become YB. Vy will become VBY, the velocity at Y point. Okay, so let's write down that equation. So between A and B, apply the projectile equation. So velocity at B and y component of that. So VBY square equals VAY square plus minus 2g gravitational acceleration YB minus YA. Now YA is is the ground position, and that's where our origin of the coordinate system is, because coordinate system is defined as x positive and y positive, and this point is 0 0. So ya is 0, yb is the maximum height h. That's what we will substitute. G is gravitational acceleration. The problem is in SI system, so this is 9.81, and initial velocity, y component of the velocity is va cosine, va sine 30. So that's the first step you should do, is you should calculate the x and y component of the velocity. So vax is va cosine 30 and vay is va sine 30. Now, what is the velocity of ball at the top? Y component of the velocity, and we have seen that through the interactive graphical figure in the previous presentation, that y component of the velocity is 0 at the top. So now this is 0. This is va sine 30, which is 10 sine 30 square minus 2 multiplied by 9.81 h minus 0. So from this equation, so by solving this equation, we'll get the value of h, which is 1.27 meters. Okay, so we have calculated the maximum height that the ball can reach. Now the second problem is also related to the same graphics, that determine the range r and the speed with which the ball strikes the ground. So we need to calculate how far the ball goes from A to C. So we need to calculate the distance from A to C, and that is along horizontal motion. So we will make use of this equation. However, for this equation we need time t, which we do not know. So first thing is we will calculate how long it takes for the ball to travel from A to C. Now A and C, they both are at the same elevation, in the sense that they both have same y coordinate. So using y coordinate equation number 4, where ya and yc are both the same, we will rewrite this equation and calculate the time t required to go from A to C. So let's apply this equation. So from going from A to C, we apply the projectile equation, and for that, yc equal to ya plus va y t going from A to C minus 1/2 g t ac square. So in this equation, both ya and yc are same, so we can say like 0 0. Vay is 10 sine 30. TAC is unknown. Gravity is 9.81. Make sure that you do not submit negative number for gravity here, because we already have considered the negative sign in the equation. So do not put negative one more time. Multiply by TAC square. So from this equation, we can calculate the value of TAC, which is 1.0194 seconds. And now we can substitute that value into this equation between A and C, and then calculate the value of maximum distance. We call this range R, or you can also call this X max, which is given by XA plus VA X multiplied by TAC. Okay, so we just substitute. XA is 0, VAX, X component of the velocity is 10 cosine 30 multiplied by time, which is 1.0194. So this time is actually this time. Okay, so that goes here. You substitute that and get the value of maximum range, which is 8.83 meters. Now the final parameter that we need to calculate is the velocity with which the ball hits the ground. Okay, so we need to calculate VC, and for VC we need to divide this into VCX and VCY. So we need to calculate both the components, and then we can calculate the magnitude using vector equation. So since the projectile motion does not change the horizontal component of the velocity, VCX is same as VAX, which is 5 meters per second, Oh, sorry, not 5 meters per second, but that's 10 cosine 30. Now, the y component of the velocity we can calculate using the projectile equation written between point A and C. So V C y component of the velocity is equal to VAY or minus G multiplied by TAC. So basically this equation is this equation number 3 here, written between point A and C, where A is initial point, C is final point. So write this equation, substitute the values VAYC, we know that value, which is 10 sine 30 minus 9.81. We already know this time 0.1094. So we get this number equal to minus 5 meters per second. Okay, and Vx is given as well, which is 8.66 meters per second. So now we have both the components of velocity. So actual velocity at Vc is square root of x component square plus y component square, so which is square root of 866 square plus minus 5 square, and we get that number as 10 meters per second Vc. So one thing you should notice here, that velocity at C is same as velocity at A with which it's being launched. So VA is 10 going up, but VC is 10 going down. Now this is true because the projectile, both A and C have the same elevation, and we do not consider any air resistance or any other like particle rotation. That's why both A and C have the same magnitude of the velocity.